Today we are explaining the paper Improving the Matrix Multiplication Exponent with Modern Optimization and AlphaEvolve.
What question is this paper trying to answer?
It asks how far we can lower the asymptotic exponent for multiplying to large square matrices. The paper improves the rigorous upper bound by redesigning the numerical optimization inside a computer-assisted proof.
What does that exponent measure in practical terms?
If the exponent is omega, multiplying to n by n matrices takes roughly n to the power omega arithmetic operations, up to smaller order vectors. The naive method is cubic, so every reduction below 3 matters, even when the improvement is only in the 4th decimal place.
What was the strongest earlier route to a better bound?
For about 40 years, improvements have relied on the laser method, which indirectly designs fast matrix multiplication algorithms. The current refinement is called combination loss analysis.
Where did that approach still leave room for improvement?
Combination loss analysis turns the proof into a large non-covest optimization problem. Earlier work solved a smaller version with sequential quadratic programming, but the search becomes much harder as the maximum recursion level grows. The optimization cost grows doubly exponentially with that level.
So what change lets this work at a larger recursion level?
The authors make the connected changes. They reformulate the optimization so it can be handled at level 4 instead of the earlier level 3, and they replace the old solver with a differentiable, gradient-based program that can run in parallel on hardware.
How much larger is the level 4 problem?
The number of optimizable parameters rises from about 25,000 at level 3 to nearly 7 million at level 4. That scale is the central reason the implementation has to be redesigned for parallel tensor computation.
What does the optimization actually represent?
It represents a recursive decomposition of a tensor associated with the Coppersmith-Winograd construction. The decomposition is organized as a rooted tree. Each node has a level, a 3-coordinate shape, and one of 6 coordinate ordering regions.
What are the shapes and regions doing in that tree?
A shape is a triple of non-negative integers that sum to the scale of its level. A positive shape can be split into smaller shapes, while a 0-coordinate marks a boundary case. The 6 regions apply the same calculation under every permutation of the 3 coordinates.
How do those local choices become one objective to minimize?
Each node receives a mass from its parent, and the split distributions determine how much structure reaches each leaf. Entropy measures how many choices are retained, while penalties account for the loss caused by combining distributions with the same coordinate marginals. The key mathematical quantity is the maximum entropy distribution with the same x, y, and z marginals as a given distribution.
Why compare distributions that share those marginals?
The marginals preserve the amount assigned to each matrix dimension, while the joint distribution describes how those assignments are coupled. Maximizing entropy over all couplings asks for the least committed distribution compatible with the same one-dimensional totals.
How does the tree-level calculation become the final exponent bound?
The retained contributions from the root, level 2, and every deeper level are added together. A separate minimum over the leaf matrix sizes determines the usable matrix dimension, and the theorem converts any feasible solution into an upper bound on omega.
What made the new numerical solver suitable for 7 million parameters?
First, the authors encode every probability distribution with unconstrained logits and recover valid probabilities with softmax. This removes the need to enforce non-negative entries on unit sum constraints directly during optimization.
And how do they differentiate through the entropy calculation?
They use the sync-Carnot algorithm to obtain the maximum entropy distributions and their Lagrange multipliers, instead of optimizing those quantities as separate free variables. Automatic differentiation supplies gradients. Implicit differentiation improves stability through sync-Carnot, and datum updates the logits.
What implementation change turns the irregular tree into something a GPU can process?
The implementation is written in Jackson changes the computation from graph node loops to tensor operations. Phantom nodes with masks make different branches fit a common layout, and specialized stages cluster similar nodes so many axes can be processed in parallel.
Does that alignment have a cost?
Yes. Masking can increase the number of stored optimization parameters by as much as a factor of 3. The trade-off is worthwhile because the resulting tensors can use hardware parallelism across as many as 10 axes, making level 4 feasible. The resulting method pipeline is therefore a mathematical objective, a differentiable optimizer, and a tensorized implementation that exposes the computation to GPS.
Where does AlphaEvolve enter this pipeline?
After building the gradient-based optimizer, the authors let AlphaEvolve modify the optimization program itself. Each candidate program runs for about 5 hours on one GPU and is scored by the omega bound it produces.
What special search design helped AlphaEvolve improve the optimizer?
They use evolving constructions. A new generation starts its optimization from the best solution found by its parent program. So code evolution and numerical search can build on one another instead of starting from scratch.
What numerical improvement does the pipeline achieve?
The gradient-based solver alone improves the previous state-of-the-art by about 0.00097, while AlphaEvolve increases the total improvement to about 0.000162. The final certified bound is omega less than 2.371177.
How should we interpret an improvement that small?
This is not a claim that one everyday multiplication suddenly becomes faster. It is an asymptotic improvement in the exponent of the best-known algorithm. The paper's comparison table places the new value below earlier milestones to 0.371866, then to 371,552, then to 0.371339, and now to 0.371177.
How do they make sure floating point optimization did not invalidate the proof?
They separate discovery from certification. After optimization, the floating point solution is rounded to rational numbers. Every derived quantity is then recomputed with exact rational arithmetic, and logarithms are replaced by rational bounds rounded in the safe direction so all constraints remain satisfied.
Does the paper claim that this optimization path will keep delivering large gains?
No. The authors say that further modest improvements may be possible, but larger advances will probably require new mathematical ideas rather than only better tuning or more efficient search.
What is the central takeaway from the whole argument?
The paper turns a previously limiting proof search problem into a level 4, differentiable, GPU parallel optimization. Gradient methods provide the scalable search. AlphaEvolve improves the search program, and exact arithmetic certifies the result. Omega is less than 2.371177.
So the advance is both a better bound and a more capable way to search for future bounds.
Exactly. That wraps up this paper explanation.